Hello everyone, welcome to my next video on System Verilog for verification. In this video, I will be discussing about another powerful feature of System Verilog, that is arrays. So arrays are helpful for handling collections of data, and they are mainly used when we write efficient and scalable test benches for design verification. So let's explore different types of arrays, their features, and how to use them in System Verilog. So this is a quick look at the agenda for this session. We will begin with an introduction to arrays and then explore its various types like fixed array, packed and unpacked arrays, and different operations you can perform on them. We will then move on to dynamic arrays, associative arrays, and queues. After that, we will do a comparison of all these array types, followed by deep understanding in array methods like find, sum, sort, etc. Finally, we will do a wrap up with a short assignment to help you practice what you have learned. So what are arrays in System Verilog? Arrays are used to group elements, multiple elements of the same data type under a single name. So it helps in organizing and accessing related data more efficiently. And each element in array is accessed using an index. So System Verilog classifies arrays into several types like fixed size arrays, also known as static arrays, where the size is defined at compile time. Next, dynamic arrays, whose size can change during runtime. Next, associative arrays. In associative arrays are indexed using keys instead of integers. Queues, which are like arrays but they are optimized for insertion and deletion from either end. And finally, packed and unpacked arrays, which define how data is stored and accessed at the bit level. So in the coming slides, we will go through each of these types one by one with examples. So fixed arrays are those arrays that have a size that is defined at the time of declaration and cannot be changed later. And because of this, memory for these arrays is allocated during compilation itself, and they cannot grow or shrink during simulation. The syntax for these arrays is very simple. Data type, then the array name, and in the brackets, we have to specify the size for the array. For example, this is a 10 elements array of 8-bit each. This is a 8 element array of type logic. To access an element, we just use its index, and index starts from 0. For example, we are accessing the 0th index for this array. So this kind of array is used when the number of elements is known in advance and doesn't change during simulation. So packed arrays, this is an important concept for understanding how data is stored and accessed at the bit level. In packed array, it has dimensions declared before the variable name. These arrays are stored as a contiguous set of bits, which makes them useful for bit level operations. In fact, in Verilog 2001, when you declare a dimension before the name, it is called the vector width. And packed arrays are often just called vectors. For example, this is an 8-bit packed array where each bit is a part of the contiguous block. So packed array allow you to divide a vector into subfields, means you can access each bit or slice individually. They can be made from various types like logic, bit, reg, enums, or even other packed arrays. So these are mainly useful when you want precise control over memory layout, like when describing registers or protocols. Now we are on unpacked arrays, which is quite different from packed ones in how they store the data and how we access them. So in unpacked arrays, we declare the dimensions after the variable name. And each element in an unpacked array is stored separately, and they are not necessarily contiguous in memory. This makes them more flexible, means you can use them with any data type, including user-defined types like structures, enums, or even other arrays. So system Verilog treats each element of an unpacked array as a separate 32-bit word in simulation. These are some of the examples of unpacked arrays. This is an unpacked array of 8 elements. This is a 2D array, 16 rows and 8 columns of integers. This is a 4 rows of 8-bit vectors. This is same as above, just different syntax. So you can see the position of dimensions define whether it is packed or unpacked. And it also impacts how the tool stores and processes them. So this is visual comparison of packed and unpacked arrays. On the left, we have a packed array. This is stored as a single contiguous vector of 8 bits, like bit 7, bit 6 till bit 0. This is ideal for bit level operations or databases where tight packing is required. On the right hand side, we have unpacked array. Here each bit is stored as an individual element in memory. So you get data 0, data 1 up to data 7, each in a separate memory location. So this is useful when you want to access or manipulate elements individually or independently. So this is very important concept and has a big impact on how the simulator handles your data. So this is an example of how fixed multidimensional arrays work in System Verilog, mainly when you combine packed and unpacked dimensions. So take a look at this declaration. It means 7:0 is a packed 8-bit vector. 3:0 means 4 such vectors per element. And 0:2 means there are 3 elements which are unpacked. So it is like a 3-row matrix. You can see here we have a 3-row matrix, and inside each row we have a 4 element because we have defined the first dimension as 3:0. So we have a 4 vectors per element, and inside each vector we have a 8 bits, 7:0. So inside each vector we have a 8 bits. So when we say byte 0 means we are accessing the first row, the first element, which is 32-bit wide. When we say byte 1, we are accessing the second row, and so on. So it would be clear from these examples. When we say byte 1 equals to this assignment, so it would assign a 32-bit value to the second row because byte 1 means second row. When we say byte 0, 1, it means from the first row, assign this value to the second vector. Second vector means because indexing starts from 0. This is the first vector and this is the second vector. We are accessing the index 1. So this 8-bit value would be assigned to these bits. When we say bytes 0 to 2, it means we are accessing the third bit of the third vector from the first row. 0 means first row, 2 means the third vector, and this 2 means the third bit. So this is the first bit, this is second bit, and this is the third bit. So you can see how indexing works at each level, and this kind of layout is very common in packet handling, FIFO design, and memory modeling. So these are various ways to initialize fixed size arrays in System Verilog. Firstly, we start with one-dimensional array. So here this is a one-dimensional array of size 2. We are assigning value 3 at first index and value 7 at second index. Nextly, this is an example of multi-dimensional array. Here we are initializing A0 with values 3, 7 and 1, and next index with values 5, 1 and 9. Next is an example of default initialization. Here all values are initialized to -1. Next is array copying, and this is allowed only if dimensions and type matches exactly. Next is an example of replication. Here 3, 2 means replicate the value 2 3 times. So at the first index, we assign the value 1, 3 and 6, and second index, we are assigning values 2, 2 and 2. In the next, we are assigning value 5 at index 1 and assigning value 1 at the third index. And all the other indexes, we are assigning value 0. Next is again example of replication. Here we are assigning value 1 and 2 two times, means replicate both this value two times. So we get the result as 1 2 1 2. And again we are doing replication, means replicate all these three times. So we are assigning all three elements of these vector with these values 1 2 1 2, 1 2 1 2 and again 1 2 1 2. So understanding all these assignments are very helpful in writing clean, readable and scalable code. So now we will see how to work with fixed size arrays using loops and functions. So first look at this example. Here we are using a 4 element 8-bit array. And the for loop here initializes this array with random values using $random. And the for each loop then prints each element with its index. Now one point to be noted here is for each simplifies the process by automatically handling the index. We don't need to track the loop bounds manually. Next is arrays can also be passed to function and task. For example, we have defined a function sum array that takes 5 element integer array and it uses for each loop to add all the elements and then it returns the sum. So the size must be specified for the fixed arrays. We have already discussed about the packed arrays. So these are the contiguous blocks of memory and they are efficient for bit level manipulations. So this is an example of the packed array, 8-bit packed array. Firstly, we are doing assignment. We are assigning a single value to the entire array. Next is the bit select. Bit select allows us to access individual bits using an index. For example, in this case, we are setting the fourth bit to value 0. Remember, indexing starts at 0. So index 3 is the fourth position. Next, we are doing part select. So part select allows us to handle a range of bits. So here we are assigning bits 2 through 5 to value f. Next is arithmetic operations. So arithmetic operations work on the whole array. For example, packed data equals to packed data plus 8-bit hexadecimal value 1 means increment the value of the entire packed data array by 1. We can also compare the entire array with the value. For example, in this case, this comparison, it checks if the array matches AA. So we are adding the conditional logic here. Now, since the size for these arrays is fixed at compile time, so there is no resizing. Means we do not have array methods like size or any iteration support. So these arrays are very powerful for hardware modeling due to their contiguous nature, and they support bit select, part select, arithmetic operations, comparison operations. But because of the lack of methods like size, etc., they are less flexible for dynamic data handling. Now let's discuss operations on unpacked arrays in systemverilog, where each element is treated as a separate entity. Consider this example. First, we are doing element assignment. So here we are assigning values to individual elements. In this case, we are setting the first element to value 1. Next, we are doing the iteration. So for loop accesses and sets all elements to 0 using an index. Next, unpacked arrays also support array methods like size, which returns the number of elements. So for example, in this case, the value 8 would be returned if we call the size method on this array. Next, like the main limitation of unpacked arrays is that we cannot perform bitwise or arithmetic operations on the entire array. All operations must be done on individual elements. Instead, packed arrays provide capabilities to perform operations on the entire array. Before moving to dynamic arrays, if you have any questions or doubts, please feel free to ask me via email or LinkedIn. So let's move on to dynamic arrays and system verilog. These are the type of unpacked arrays whose size can be set or changed during the simulation time. So let's see how to create these arrays and how they fulfill our runtime needs, what are their key features and what are their use cases. Firstly, the new operator is used to set or change the array size. So this allows us to allocate memory dynamically, which is perfect when the size is not known at the compile time. Secondly, the size built-in method, it returns the current number of elements. So this is very useful while array tracking. Next, the delete method, it clears all the elements, reducing the array to zero size, an empty array, which is useful for resetting or reusing the array. Now, why would you use the dynamic array? In verification, we may need array whose size varies based on some behavior. For example, Ethernet packet lengths can range from say 64 bytes to 1518 bytes per packet, and dynamic arrays are capable of handling this variable length. Finally, the size for elements is allocated at runtime. It is not fixed upfront. And the syntax for dynamic arrays is very simple: type name, array name, and the subscript operator. You can see no initial size is mentioned here. So now let's understand how to define, allocate, initialize, and do other operations on the dynamic array using this example. So here we have declared an initial array, and you can see we have not specified any size. Next, we are allocating memory for 5 elements, indexing from 0 to 4 using this new operator. So this sets the initial size dynamically. For initialization, we are using a for loop. Inside this for loop, we are setting each element to a multiple of 10 based on its index. So, and it uses the size method to get the current size. Alternatively, we can use inline initialization also with this statement. So here we are allocating memory for 3 elements and directly assigning value to the 3 elements. In resizing, we have two options based on whether we want to retain previous values or not. With this statement, we are expanding our array to 10 elements and we are retaining the old values also. But if we are using this statement, then we are expanding to 30 elements and the old values are lost. Finally, we are using the delete operator for deleting the array, and it frees the memory, resetting it to an empty state. So this example shows the power of dynamic arrays. Firstly, we are defining with no initial size, allocating with new operator, initializing with loops or inline values, resizing with retention or overwrite, and finally cleaning up with delete. So these features makes them very handy for verification scenarios. So let's walk through a complete example of dynamic arrays in System Verilog. We start by declaring a dynamic array with this statement. So here we have not specified any size. Next, we are allocating memory for 4 elements indexed from 0 to 3. Nextly, we are using a for each loop, and inside this loop we are initializing the array with values 1, 2, 3 and 4. And the size method confirms we have a 4 elements. So the $display statement prints the original array size. Now moving to resizing. So here this statement resizes the array to 8 elements and it retains the old values. And we manually set value 5 and 6 to index 4 and 5 respectively. So the $display statement here shows the updated size of the array. So we can see in the diagram also, initially the size of the array was 4, having values 1, 2, 3 and 4. Nextly, we have resizing it to size 8. So the 4 more elements are added in the array, and we manually set values 5 and 6 at the index number 4th and 5th. So now finally moving to the next statement, that is delete. So this statement clears the array and set it to empty. So the $display statement here, it confirms the size is 0 and it frees the memory. So now let's move on to associative arrays in systemverilog. These are a step beyond the dynamic arrays, and they offers unique advantages for handling sparse or unknown sized data collections. Firstly, dynamic arrays are great for contiguous collections where the number of elements changes dynamically. But when the size is unknown or the data is sparse, means many indices are unused, then associative arrays are the better fit. The main feature of associative arrays is that they do not allocate storage until an element is used. So this saves memory, especially for large sparse data sets. And the elements are stored in an order that ensures the fastest access. And they are optimized internally by the simulator for efficiency. The syntax is very simple: data type, array name, and the star inside the subscript operator, where the star indicates an wildcard index. And this allows flexible indexing. Index can be of any type: string, integer, or a class. Real and short real are not allowed. If the index is specified as star, then the array can be indexed by any integral expression of arbitrary size. So associative arrays are mainly used for sparse or non-sequential data, where the memory is allocated dynamically and not contiguously. So this is an example of associative array. In this example, we are using string as the key and we are assigning values to the specific keys. In the next example, we are using an integer key and we are storing a 8-bit value at index 100. So you can see the comparison between standard array and associative array. In standard array, all the memory is allocated, including the unused elements. So we are only using index 0. Index 1 is unused. We are using index 2. Then 3, 4 and 5 are unused. Then we are using index 6 and 7. But the memory is allocated for all the indexes. So it is wasting memory on empty slots. But in case of associative array, it only uses memory for defined elements. So for index 1, index 3, 4 and 5, we have not allocated any memory. So these are the perfect for scenarios with irregular data access. So let's discuss the methods available for associative arrays in systemverilog. These methods are very helpful for managing sparse or non-sequential data. So starting with num or size, this method returns the number of elements currently present in the associative array. Next we have exist method. So this method checks if an element exists at the specified index. It returns 1 if element is present and it returns 0 otherwise. So this is very good method, very useful method for validation. Next we have a delete method. It removes an element at a given index. If no index is specified, then it deletes the entire array. Next we have first method. It would return the value of the smallest index in the array. So it is very helpful when you want to start an iteration, then it will return the smallest index from where you can start the iteration. Similarly, the last method, it does the opposite of the first. It returns the value of the largest index. So it is very useful for traversing from the end. Next we have a next method. This method returns the smallest index whose value is greater than the given index. And in case of priv method, it returns the value of the largest index whose value is smaller. So these methods are very useful for navigating the array in order. And all these methods provide good control over associative arrays. So this is a practical example of associative arrays in System Verilog. Here we have a module named test which shows insertion, displaying, checking key existence and deleting the entries using associative arrays. Firstly, we start by declaring an associative array with string indices. In the initial block, we are inserting the data. We are using the key values as ASIC and Guru, and we are assigning values to these keys as 1 and 2 respectively. So next we are using the first method to get the first key. And inside a while loop, we are using a next method and it iterates through all the keys, displaying each with $display. So it would display the content as key is equal to ASIC, value equals to 1. And the next iteration it would print key equals to Guru and value equals to 2. Then we are using the exist method to check if the key ASIC present or not. So as this key is present in the array, so it would display key ASIC found. Finally, we are using the delete method to remove the key entry Guru. Now we are displaying the total size of the array. So the total size is now 1 since we have deleted the one entry from the array. So let's now talk about queues in System Verilog. Queue is a variable size data structure that is used to store homogeneous elements, that is elements of the same type. It behaves like a one-dimensional unpacked array and it can automatically grow and shrink in size. Queues allow insertion and deletion of elements at any index, which makes them flexible for dynamic operations. Another key feature of queues is that they offer constant time access for reading, writing, and for insertion of elements both at the front and at the back. In System Verilog, the index 0 always refers to the first element of the queue, while the special symbol dollar represents the last element of the queue. Queues can be used to implement both LIFO, last in first out, and FIFO, first in first out behavior, depending on how you manage the insertion and deletion operations. The syntax to declare a queue is type, name, and the dollar inside the subscript operator. So here we have a few examples. So the first example, it declares a queue of integers. And in the next one, we are creating a queue where each element is 8-bit wide. So queues are especially useful when you don't know the size of your data in advance or when it needs to change dynamically during simulation. So we can declare queues in two different ways. The first is unbounded queues. They doesn't have any fixed size and they can grow or shrink dynamically as needed. For example, this is a declaration for an unbounded queue. So using this pushback method, we are adding an elements. So we can keep adding elements using this method and the queue will automatically increase in size as new elements are added inside the queue. Next, we have another method to declare a queue, that is bounded queue. In bounded queue, we have a fixed maximum size and it must be specified at the time of declaration. For example, here we have declared a bounded queue with a maximum of 3 elements 0 to 2. So we are adding elements using pushback operation. We are firstly adding first element, then second element and then the third element. Since the size of the queue is set to maximum 3 elements, so when we try adding the fourth element, it would give an error, say queue is full. Bounded queues can also be declared using this syntax, low:(high) syntax, and the size is calculated as high minus low plus 1. So let's now explore some of the commonly used methods in System Verilog queues. So to explain each of the method, we are using this example. Here we have declared an unbounded queue and we have added elements 0, 1, 2, 3, 4, 5, 6. So the total size of the queue is 7. So firstly, we have a size method which returns the number of elements in the queue. So here queue.size would return value as 7 because there are 7 elements in the queue. Next, we have an insert method which allows us to insert an element at a specific index. For example, it would insert a value 9 at index number 2. You can see the 9 is inserted at the second index. Next, we have a delete method. It would remove an element from the specified index. For example, when we call this, the item would be removed from the fifth index. So fifth index is this one. So value 4 is removed. Next, we have a pop front method which would remove the elements from the front of the queue. So the front of the queue is 0. So it would return 0. Similarly, we have a pop back method which removes the element from the end. So element at the end is 6. So it would return the 6. Next, we have a push front method which would insert the element at the front. And similarly, we have a pushback method which would add an element at the end. So here, if we are passing 8, the 8 is inserted at the front, and we are passing 0 and the 0 is inserted at the back. So all of these queue methods are very useful for dynamic data manipulation in system Verilog, especially in test benches and verification environments. So this is a complete example of how queues work in system Verilog. So here we start by declaring an unbounded queue using this statement. It means queue can grow or shrink dynamically. In the initial block, we are performing a few operations to manipulate the queue. So here in the first statement, we are adding 10 at the end. Then we are adding 20 at the end, and then we are adding 5 at the front. So now our queue looks like 5, 10 and 20. We are displaying the queue contents and it would print the full content as 5, 10 and 20. Now we are accessing the specific elements in the queue. Firstly, we are accessing Q0. It would give the first element, which is 5. Q$, it would give the last element, that is 20. Then we are removing the front element from the queue. So it would remove the 5. Then again we are displaying the contents of the queue. So it would now print values 10 and 20 because we have already removed 5. Finally, we are calling the delete. It would clear the entire queue. Now we are printing the size using the size method. So the size would be now 0 because we have already deleted the entire queue. So with this example, you can see how flexible and dynamic the queue is by using all this pushing, popping, accessing and deleting methods from the queue. Let's quickly go through some of the key advantages of using queues in system Verilog. Firstly, there is no need to predefine the size at the compile time. Queues are flexible and they automatically grow or shrink based on your needs. Secondly, the user does not have to manage the size information manually. Whenever elements are added or removed, the queue automatically resizes itself. Thirdly, even though it is dynamic, the access time is very similar to static arrays. So there is no performance penalty. Next, queue comes with built-in method for common operations like data processing and analysis. So it makes them very efficient and very convenient to use. Next, there are also inbuilt methods for operations like computing the sum of the elements or sorting the queue. So we don't need to write the extra code to perform all these operations. Searching through queue is also very simple even if you use the complex expressions. Finally, queues are a perfect fit for first in first out or last in first out modeling, which is very useful in hardware verification. So till now we have discussed all the four type of arrays available in System Verilog. Now let's compare each of them. First we have a fixed arrays. So fixed arrays are those arrays where the size must be known at the compile time. And they're best suited for contiguous data and for small memory sizes, typically ranging from 1 kilobyte to 1 megabytes. So fixed arrays cause memory wastage, but they offer fast access time since the index is directly mapped. Now next move to dynamic arrays. So in dynamic arrays, the size is allocated during runtime. And they're ideal for storing sequential collections, and they can handle large memory sizes over 1 megabytes. So they offer a good balance of memory usage as well as performance. Next we have associative arrays. They are also allocated during runtime, and they are useful when data is irregular, when data is sparse or non-contiguous. There is no memory wastage since elements are stored only when needed. So no allocation is done if element is not used. But the performance is moderate compared to fixed or dynamic arrays. Last we have queues. These are like dynamic arrays but with additional power that they can grow and shrink automatically. They are perfect fit for modeling FIFO or LIFO behavior, and they are ideal for big memory operations where both performance and manipulation are critical. So queues provide the best combination of memory, efficiency, access speed, and ease of use. So queues are the best choice. But depending on your use case, whether it is predictable storage or flexible data access, each type of array has its own strength or has its own drawbacks. So next we have array query functions. So in System Verilog, we can extract a lot of information about arrays using these functions. So let's consider the following two-dimensional array. Here we have the first dimension 3:0 and it has indices from 3 down to 0, and we have a second dimension, it has indices from 1 to 4. Now let's go through each of the methods. First is $left, it returns the leftmost index. So here we are passing the dimension as 1. So for the dimension 1, the leftmost index is 3. Next is $right, which would return the rightmost index of the specified dimension. So here with the first dimension, the rightmost index is 0. Next is $low, which would return the lower bound of the specified dimension. So here we are passing the dimension as 2, and for this dimension the lower bound is 1. Next is $high, which would return the higher bound. Next we have $increment, it would return the direction of indexing. So here we are passing the dimension as 1. So for the first dimension, the direction of indexing is in descending order, it is decreasing, so it would return the value as -1. Next is $dimension, it would return the total number of dimensions in the array. So here we have 2 dimensions, so it would return the value 2. Next is $size, it would return the number of elements in the given dimension. So here we are passing the dimension as 1, so it would return the size as 4. So next we have array locator functions, and these are very useful functions for searching through arrays based on some conditions. So let's consider this queue example. Now let's explore each of these methods. First we have a find method. So this method returns a queue of all the elements that matches the condition. For example, we are calling this method with this condition queue.find with item greater than 20. Means it would return all the elements from the queue having values greater than 20. So it would return value 45, value 32, and then value 45. Next we have find index. It would return a queue of indices of all the elements that matches the condition. So for this example, it would return all those indices where item value is greater than 20. So again, we have this value at index 1, then this value at index 3, and then index 4. Next, we have find first. It would return the first element that matches the condition. For example, q dot find first with item less than 15. So we have the first element, this, which matches this condition, so it would return 12. Next, we have find first index, so it would return the index of the first matching element. So here the condition is item equals to 45. So this condition is match here at this index. So we will return the index is 1. Next, we have find last. It would return the last element that matches the condition, and similarly we have find last index, which returns the index of the last matching element. So the important point to be noted here is that the with close is mandatory for all these functions. And these locator functions they are very useful when filtering or when searching data structures efficiently. So next we have locator and ordering functions that help us analyze and organize data in system Verilog. So first we have a unique method. So it returns a queue of unique elements from the array and removes all the duplicates. Next we have a min. It returns the minimum value in the array. So it is useful for quick comparisons. Next we have a max. It returns the maximum value. Next is reverse. It reverses the order of elements in the array. So say if your data is in ascending order, then this function would flip your array to descending. Next you have sort. It would sort the array in ascending order, lowest to highest. And rsort sorts the array in descending order, means highest to lowest value. Next we have shuffle. Shuffle randomizes the order of elements in an array. So it is mainly useful for test cases or simulations where order should not be predictable. So all these functions make it easy to manipulate and organize data with just a single line of code. And they are very helpful in test benches and data analysis. So next we have array reduction functions in system Verilog. So these functions operate only on unpacked arrays and they always return a single value. So let's consider this simple example of queues. So first we have a sum method. It would return the sum of all the elements in an array. For example, q.sum, it would return the sum of all the elements, that is 12. Next we have a product function. It would return the product of all the elements. Next we have an AND. It would perform a bitwise AND across all the array elements. So this is useful when you are checking if a certain bit pattern is set across all the elements. Next we have a OR. It would perform a bitwise OR across all the elements. Next we have a XOR. It would return the result of a bitwise XOR of all the elements. So these reduction methods are helpful when you are performing operations across an entire data set, like summing up the values, checking bitwise conditions, or combining some flags. So let's look at an example of all the array methods which we just discussed. So firstly, we are starting by declaring a dynamic array and initializing it using inline initialization. So inside the initial block, firstly we are using the method find, and we are trying to find a number which is even, which is divisible by 2. So the first number which is divisible by 2 is 10. So $display would print the value as 10. Nextly, we are using the method find index with the condition that we are trying to find a number which is divisible by 3. So the first number which is divisible by 3 is at index 1. So $display would print the value as 1. Next we are using the method sum, and it would print the total sum of all the elements. Next we have a method OR. So it would perform a bitwise OR on all the elements. Since all are non-zero, so the $display will output 1, indicate that at least one non-zero element is present in the array. So this is a simple assignment which tests your ability to define array types and implement all array methods. So firstly, you need to define three array types: a fixed array of size 1024, a dynamic array initially set to 1024, and an associative array with an integer index. So next, write to the locations 0, 50, 100, 200, 500 and 1000 in each array. So this tests how each type handles non-sequential data, non-sequential access. So moving to the next question. Now determine how many elements are allocated after the write. So for a fixed array, it is always 1024. A dynamic array will allocate 1024 initially, but only uses 6 elements after the writing. An associative array uses memory only for the 6 specified indices, so making it efficient for sparse data. Now your task also includes writing programs to demonstrate all methods of fixed arrays, dynamic arrays, associative arrays, and queues, covering everything from size function to find function. Finally, I will suggest you to read the System Verilog LRM to deepen your understanding of all these methods. In case of any queries or questions, please feel free to connect me over this mentioned email ID or LinkedIn. Thank you.